Okay, graphing the complex numbers in the complex plane. Remember, complex numbers are written in the form a plus bi, where a is the real number and b is the imaginary number. And in this plane, the real numbers are on the horizontal axis and the imaginary numbers are on the vertical axis. When we're looking at question A, the point is -1, 3. Part B is -4, -5. Part C, there is no I, so that's as if you had plus 0i. That's the point 3, 0. And part D, there is no constant term without an I. That's as if you had 0 plus 4i, and that's the point 0, 4. Plotting those points, the first point, -1, 3, means I go back 1 on the horizontal axis and up 3 to the positive imaginary axis. That's point A. -4, -5, I go back 4 on the horizontal axis and down 5 on the vertical axis. That's point B. 3, 0, I go to the right 3 and stop. That's point C. And 0, 4 means I just go up 4, and that's point D. Finding the modulus, which is shown by taking the absolute value of z, is found by taking the square root of a squared plus b squared. And remember, it is the distance between the point that you have from the origin 0, 0 in the complex plane. For this question, z is given. We have -5 minus 12i, and that's written in complex form. Remember, that's a z equals a plus bi. In this question, a is -5 and b is -12. So finding the modulus, we take the square root of -5 squared plus -12 squared. -5 squared is -5 times -5, which is positive 25. -12 squared is -12 times -12, which is positive 144. The modulus is then the square root of 169, or 13. Part B, z equals 4 plus 6i. A is then 4 and b is 6. Remember that the b term is always the imaginary term and a is always the real term. The modulus is then the square root of 4 squared plus 6 squared. 4 squared is 16. 6 squared is 36. The square root of 16 plus 36 is 52. 52 has a perfect square inside of it. That is the same thing as 4 times 13. 52 is 4 times 13. I can break that up and write that as square root of 4 times the square root of 13. And the square root of 4 is 2. So that is the square root of 52 is the same thing as 2 times the square root of 13. Moving on, we're going to be writing the complex number in polar form. And in order to write a complex number in polar form, we need to remember that when we have z equals a plus bi, that is the same thing as z equals r times cosine theta plus I sine theta. I then need to convert a's and b's into r's and thetas. And we know that a is equal to r cosine theta, it's like the x component, and b is equal to r sine theta, like the y component. A is the real, which is similar to the horizontal axis, and b is the imaginaries, which is the vertical axis. We also know that r is equal to the square root of a squared plus b squared, and we know that the tangent of theta is equal to b over a as long as a isn't equal to 0. So we're going to use those properties to go from polar form to rectangular form and rectangular form to polar form. Let's start out with a, where we have that z equals 1 minus I. That means that a is 1, it's the real portion, and b is -1 because there is no number in front of the I, it's a 1 and there's a minus sign. So we're going to start by finding r, which is the square root of a squared plus b squared. 1 squared is 1. -1 squared is -1 times -1, which is positive 1. R is then equal to the square root of 2. Finding theta, we take the tangent of theta equal to b, which is -1, over a, which is 1, which means the tangent of theta is equal to -1, or the inverse tangent of -1 is equal to theta. Using the unit circle, I need to find when the tangent is equal to -1, but note that our point is in the fourth quadrant because it is a positive a and a negative b. So looking real quickly at this graph, that's the point 1, -1. And so my angle theta is going to need to be in the fourth quadrant. And that happens at 7 pi over 4. That is when your x value is positive and your y value is negative, and they're both square root of 2 over 2. Now that we have the r value and the theta value, we can write z equals √2 times the cosine of 7 pi over 4 plus I sine 7 pi over 4. For part B, we can identify A as 3 and B as 4. This is in the first quadrant. R is then equal to the square root of A squared plus B squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and the square root of 25 is 5. Now, the tangent of theta has to be equal to 4 over 3, or the inverse tangent of 4 over 3 is going to give us theta. But unfortunately, we don't have a 4 over 3 in our unit circle, and so to leave it in tangent inverse of 4 over 3 is best. The way in which we write that is then going to be z is equal to the r value of 5, cosine of theta, and for theta we're just going to write inverse tangent 4 over 3 plus I sine inverse tangent 4 over 3. Now let's go from polar form to rectangular form. We are given that r is equal to 6 and theta is equal to 150 degrees. Because when z is written in polar form, it is of the form r cosine theta plus I sine theta. That means that the value in front of the parentheses is the r, and the value after cosine and sine is the theta. I then need to find what a and b are, and recall that a is equal to r cosine theta and b is equal to r sine theta. A is then equal to 6 times the cosine of 150, and b is equal to 6 times the sine of 150. Using the unit circle, the cosine of 150 degrees, which is 5 pi over 6, is equal to -√3 over 2, and b is equal to 6 times the sine of 150 degrees, or 5 pi over 6, which is 1/2. Simplifying, 2 goes into 2 once and 6 3 times, so I can write a as -3√3, and b is equal to 6 over 1, 2 goes into 2 once, and 6 3 times, that is 3. So z equals -3√3 plus 3i, because z equals a plus bi. In this question, we're given z1 and z2 in polar coordinates, and we're asked to find their product written in polar form. In order to do this, we need to remember what the product is. If I have z1 times z2, I can take r1 times r2 times the cosine sum formula plus I times the sine sum formula. And remember, in the lesson, we proved using the sum formulas for sine and cosine why this is true. Let's identify in z1 r. r1 is 3. In z2 r, r2 is 2. In Z1, theta 1 is pi over 12, and in Z2, theta 2 is pi over 6. Let's plug those values in. The product Z1 times Z2 is then equal to 3 times 2 times the cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Simplifying Z1, Z2, 3 times 2 is 6. Cosine, adding pi over 12 and pi over 6. I can do this. I'm going to find a common denominator. I'm going to make pi over 6 into 2 pi over 12 by multiplying the numerator and the denominator by 2. That means 1 pi plus 2 pi is 3 pi over 12, which reduces by 3 to pi over 4. That means I have cosine pi over 4 here, plus I sine pi over 4. The question asks me to write my answer in polar form, which we did. That's polar form. You've got cosine theta plus I sine theta times r. Skill practice 6, we are now asked to find the quotient. Let's recall the quotient formula. Z1 over Z2 equals R1 over R2 times the cosine difference plus I sine difference, as long as R2 isn't equal to 0. Let's identify R1 equals 18, R2 equals 2, theta 1 equals 75 degrees, theta 2 equals 255 degrees. And let's substitute in our values. Z1 over Z2 equals 18 over 2 times the cosine of 75 degrees minus 255 degrees plus I sine 75 degrees minus 255 degrees. Simplifying, we're going to get some negatives, which means we're probably going to want to use even and odd properties. 18 divided by 2 is 9. And then we have the cosine. 75 degrees minus 255 degrees is negative 180 degrees. Plus I sine negative 180 degrees. Z1 over Z2 is then equal to 9. The cosine of a negative theta is equal to the cosine of that same theta because it's even. But the sine of a negative theta is equal to the negative sine of theta because it's odd. That means we have cosine of 180 degrees because it's even, minus I sine 180 degrees because sine is odd. And that is written in polar form with degrees.